It's just going to be one homework out of chapter 4 and 5. Chapter 4 introduces different forces and chapter 5 applies all those forces including the friction force. So I have combined these two chapters. You won't see when you start this, you can treat it as one chapter. When you start chapter 4, you might see some of the topics in your notes that could come from chapter 5. We have gone over one force, normal force, and we have done some examples related to it. We have seen it when the object is in the accelerating body, then how the normal force would be affected. The next force that is in line is the tension force. Tension force is a force which is, you probably are more familiar with it compared to the normal force, that maybe you have it in your mind related to the ropes, strings. You try to pull a string, so there must be some tension produced in it. In terms of physics language, yes, tension is the same whenever there is a force applied on rope, string, something you're pulling on, pushing, that results in the production of the tension force in that string or rope. For example, there is a boat and there is a rope attached to that boat and someone is pulling on it, okay, trying to pull the boat with the rope. There is a force. If I only draw the rope, there would be a force on that rope by the person. There is definitely going to be a force on the person due to the rope, due to the Newton's third law. But if I'm only putting together the forces on the rope, so there must be a force on that rope for pulling the boat. There must be a force acting to the left-hand side. And then there is a force on that rope by the boat as well. And then there would be, due to Newton's third law, there will be a force on the boat due to this rope. They should be equal and opposite. But if I'm only drawing the rope, I'm only drawing the forces on that rope. These forces, they act on both sides. So wherever the connections are present, there is a tension force. So tension force always arises from the point where the objects are making connection with each other, and it runs with the same magnitude throughout. So the tension which is produced here should be equal to the tension which is produced here in magnitude, but they could be in opposite direction. Okay, so the total force on it, the total force on this end and this end would be treated as based on the direction of tension force right at that point. What if the rope is very heavy? What do you expect? Because of gravity, so there must be like some sort of center point, and then there would be a gravity force, right, which should pull down on it, so the rope should sag, right? The sagging does come from the gravitational force, or the rope is very heavy. So in that case, there should be a downward force. So the net force on the rope should be 0. However, there would be a downward force which will result in the sagging of the rope. Now consider if the rope is not too heavy and it has a negligible mass. If it's very light rope and mass is 0. So it does not accelerating, so it doesn't matter it is accelerating or not. The total force on it would be 0 anyway because of the mass. If we consider that it's a very light string, it doesn't have a mass, and most of the problems that you will do in this course, you will use the ropes which have negligible mass, and you will not consider any gravity force making any impression on the overall forces. Okay, so the net force on the rope should be equal to 0 according to Newton's second law, and that remains 0 because there is no mass to consider to apply gravity. So there would be no net force on that rope. So when it comes to the practical problems, we draw the tension force. For example, you have a situation, you have, let's do the simple one. There would be a weight force downward, so there is like a ceiling fan or mass attached with some mass attached with some support. So this string, if we consider this is massless, where do you think I should draw the tension force? By the way, this is not a string. This is my arrow for the weight, okay? This is the string. So where do you think the force should act? Should I put the normal force here? Something hanging from the ceiling? No. Which force do you think should be there? Tension force, right? And it should be there because something is pulling on it, and we know that that is the force which will keep it stiff. If there is no force on it, this would be just hanging here. But as soon as you put the weight here, that keeps the rope stiff. So which way do you think I should, so right at that point, which way do you think I should draw the tension? Sorry? At this point? Exactly. It should be upward. Right at the point of application, it should be pointing away from it because it's pulling on the rope. Okay? So the force would be upward force. There would be a tension force up there too, but we may or may not need it. Okay? So there should be a tension force on this end, which is acting downward. So wherever you have these, like I told you, the connection point, it would always be acting away from those connecting points. So tension direction does not always be the same. It doesn't look like the same, always rightward or leftward. It really depends how you have connected the object, but it's always pointing away from the connecting points. What else? If I place this in a accelerating object, it's accelerating upward. So it's like you have an object hanging from the ceiling of the elevator. Okay, we have done it for the normal force already. So when you have a normal force, you have already treated that example. What if this elevator is accelerating upward? There is a mass which is hanging from the ceiling. It does have a mass. Due to mass, there is a weight related to it. And then there is a tension force which is acting upward. Do you think you can go ahead and solve it and give me the value for T in terms of mass, acceleration, and G? Did anyone try doing that? Is there any horizontal force? No. Only vertical, right? So we have two forces. T is upward minus mg, right? We don't put A in there because A is the overall acceleration of the whole system with the mass hanging and the elevator. This is m a y t minus mg, right? T is something that I want to separate out. This is what I asked you to do. So adding this on both sides, this gives you m a y plus m g. That means the tension will increase. T, or taking m common, a y plus g. Okay, so tension has to be higher because there is a downward force which is acting in opposite direction. So to compensate it, tension should go up. Now if I tell you this acceleration is 3 meters per second and tell you, okay, this is 10 kg block, you are all set. You can just plug in these values here. This is 3 plus 9.8, and you can solve them together. Right? So all you need is two pieces of data. 3, what should be the acceleration, what should be the mass, or the weight of that object. You could have solved this problem in terms of number. You could have found what tension should be acting here in order to compensate for the gravity. What's the answer? Huh? 128? Newton. It's a force. Okay, so it goes with the unit of force, like the normal force. All right, good. You did an experiment this week. What was that? Atwood machine in lab. Did you understand the tension in it? Was there tension involved? That was involved. But did you have to solve it directly? No. So describe that. What was the Atwood machine? That is an example of acceleration related to the objects which are connected, right? If you remember, two masses or two hangers were connected to each other by a string, right? And they could move together. Did they have different acceleration? No, they had a common acceleration. One acceleration was downward and one acceleration was upward. So you had a pulley. There are two masses. One has to be higher than the other so that the system can move. Okay, let me use the same one. They both had the common acceleration because it is one system. It's just moving. It just divided into two parts. One is on the right-hand side, one is on the left-hand side. You have the other forces which will be treated separately on both ends. Now, I can draw two forces here, right, without asking you. It is M2G and this is M1G. Correct? Right? Gravity. What are the other forces that I should put there? Friction, where? If I consider that this pulley is frictionless, and this is what you tried doing it in the experiment, right? Making it frictionless. So if the friction is not there, what other forces should be there? Tension force, right? Which way it will act? Here, upward, through the length of the string. It will act upward here as well in the length of the string. Tension force is acting at these points too, okay? But since we are not really concerned, we are not working with the pulley or this system here, this part of the system, we will not worry about that. We will only look at this mass and this mass because we want to know how the system is accelerated. If it is accelerated to the right, A here is downward negative, right? A here is upward positive. Good? Forces on the right hand side, T minus M to G, right? Exactly the same thing I did before. There is acceleration which is downward, so negative MA T minus M to G, right? If I take the T out, that would be equal to M to G minus MA. Correct? I added M to G on both sides. Right? So I have one equation in T. Is tension same? Same direction. It should have this, it's the same rope, it will have the same magnitude throughout this length. T for the other side, T minus M1G is equal to MA. Here the acceleration is positive because it's moving upward. So T will be equal to MA plus M1G. By the way, I think I didn't put the M2 here. It should be M2 here as well. Here it's M1A. This is M1A. Because we are only talking about a single mass at a time. So we found out what's the net force on this mass M2. We found out what's the net force on this mass M1. And found T. Since T is the same in both, if we compare 1 and 2, we can say these right-hand sides are equal. M2G minus M2A equal to M1A plus M1G. Right? it looks like something which is very complicated, but in fact it is not complicated at all. This just using the basic idea of tension being the same throughout the string, acceleration being the same throughout the string as well. Solving them together, I'm going to put the A's, combining A's on one side, G on the other side. So that would give me maybe I could use this side again. M1 plus M2 A M2 minus M1 G. Is that right? Are the signs good? Good? Okay. Leaving A here, M2 minus M1 G divided by M1 plus M2. That is the acceleration of the Atwood machine. You used it. That is the expression, the way it is derived using the idea of tension in the rope and finding the acceleration of the connected objects. If we have the acceleration, can we find the value of tension in terms of masses and gravities? Yes. Tell me what you get. Plug that into any of the equations that you have already for tension. You can either use 1 or 2. So either use this 2, replace this A by this equation and solve it. This is algebraic solution. There are no numbers. You did something? I'm using this second one because that's the one I can see on the board. But if you had used the first one, that should be okay. M2 minus M1 G divided by M1 plus M2 plus M1 G. Right? So I just replace A by its known value, multiplying them. Now it's going to be little bit more calculation. M1 M2 G minus M1 square G divided by M1 plus M2 plus M1 G. this gets multiplied with this. From here on, it's just math. There is no physics. M1, M2, G minus M1 square G. If I take the LCM, so this gets multiplied with this. So M1 square G plus M1 M2 G divided by M1 plus M2. These two get cancelled. They are the same. These two add up to M1 M2 G divided by M1 plus M2. That is the formula for tension for the connected object. From here, you have to take the LCM because you need to solve them, right? This one is already in the denominator of this one. This one will get multiplied with this. LCM.
So you have a common denominator. Like adding fractions.
If you had this, how would you take, yeah. Yeah. So if you have this, what would you do? Right? How would you solve this? 1 plus 18 over 9, right? Exactly the same thing I did there. It's just symbolic. Do you see something like that in maths? You do. You do. It's just when we put the masses there or gravity there, it just throws the whole idea away. Even though it is all the same, it doesn't make any difference. Okay? So try to understand this by simple example. Okay? Mm-hmm. And this is a sort of problem that I can give you on the exam. Because it was physics as long as we were talking about tensions and the weights. It is maths now. How did the lab go? Large errors? You did? No? Okay. But you figured that out, right?
Yeah.
No? Okay. All right. Next. After tension, after giving you enough tension, we have friction force. What is friction? Where does it come from? It comes from the way the surfaces are, from the roughness of the surfaces. When you put two surfaces together, the surfaces are not very smooth. So there is an intermolecular interaction between the surfaces. That results in interlocking of these two surfaces. So friction is a quantity which does depend on the type of surface. Okay, if you have steel or you have steel here, you have mirror or cement here, cement versus cement. So it really depends on the type of surfaces that are being moved on each other. Friction is present, it's a culprit It is present almost anywhere you could think of. In fluids, there could be less friction in fluids, but the fluid friction still exists. So if when something is in contact with the other object, there is one force which you know, that normal force. Normal force is just coming because of the pushing of the object, one object on the other object. It is active even though there is no force on it. Friction is not active yet. Okay? It becomes active if I apply a force on that. Okay, so there is a difference in these two forces. Normal forces exist just because the objects are in contact. Friction force does exist, but it doesn't play any role as long as there is no force acting on it. When the force is applied, friction force right away between the surfaces, it starts acting in the opposite direction. Okay, that means you have, let's say you have 5 Newton, you apply force 5 Newton, there is a 5 Newton force on the other hand. Will the object move? You apply 5 Newton, quickly 5 Newton force is there due to friction. It wouldn't move, right? There is no net force. You increase the force to 10 Newton and the friction goes to 10 Newton and the block still doesn't move. There is a limit, okay? There is a limit that you can hit where you have to stop and the friction has to decrease. As long as it doesn't reach that limit, for example, it has gone to 15 Newton, now the friction is 11 Newton. Yes, the block would move to the left. Okay. Now, why it didn't cross this limit? Why it cannot go more than that? That is the limiting friction, okay, which stops the object from moving. If I plot these forces together, friction force versus applied force, friction force, you apply the force, friction force increases with it, but it will increase to an extent where it cannot resist no more and it has to move. And it does have a value to it. After this limit, it moves. What do you think about the friction after it starts to move? Should it be the same? Or it has lowered? Yeah, and it has started to move now. That means friction is not bothering it that much, right? As it was playing a role before, it decreased to a value. That is called the kinetic friction. This friction called static friction as long as the object has not moved. This is called static friction. Static friction does have a limiting value. What do you think, if I ask you before giving you anything, what do you think friction should depend on? Surface area? You mean more surface area, more interlocking between the surfaces, more forces? Okay. What do you mean by that? Force, external force? But that.
This is like if there's active force going on one side of the surface, like if one's stationary, another one's moving. That would be where it contact.
So the applied force and the friction force, they increase with each other. You put more force there, friction goes up. I mean, you can see that kind of dependence. But in terms of the block characteristics, like if you just look at the block and tell what could be there which is not letting it move. Mass? So the heavier object should have more friction? Yeah. Type of material should matter? You probably find it easier to put a mirror on the mirror and move it, right? Compared to two very rough surfaces. So type of surface, yes, we have a common point. Yes, we can agree on that. Mass, what do you think? One set contact area. If you increase the area, friction increases. That's what's said so far. What do you think about when there is a mass, is there another force too? Gravity, yes. I mean, mass is not the force. Gravity is the force related to mass. Is there any other force other than gravity? A normal force. Normal force is pushing on that surface, right? So what do you think about if something is sitting on the flat surface? I think we have already did this example. If I make it inclined, do you think friction in that case is less than the friction in the bottom case? It can slide, right? If you keep increasing the angle, it will eventually slide. Probably friction here was less than the friction that experienced here. But mass is still the same in both cases. So what happened? Normal force changed. Okay? Now, based on the experimental work, it's been seen it is proportional to the normal force. Okay, now that is experimental evidence. Okay, if we think about the friction, his thought process is correct. The way he's thinking, more area in contact, more interlocking, yes, that should produce the mode. But this is not what has been observed experimentally. Experimentally, increasing surface area does not change friction. Changing normal force changes friction. That means more the surfaces are pushing on each other, the greater will be the friction force. If I take the proportionality sign away, that gives me, I didn't put anything yet, I'm going to work on it. This gives me mu s n. This is called coefficient of static friction. Mu s. That depends on the surface. Type of surface. What type of surface? Not the shape or like size or some other characteristics. It depends on the what kind of surface you're talking about. Typical material. What material it has been made up of. Also, is this friction value always equal to this? Right from the beginning? Or less? You apply a force, it could have a smaller value. Then it increases. Here, it reaches to a point where it has become mu Sn. It can't resist anymore. It's the limiting value of this friction. So friction force could be less and equal to mu Sn. Okay? When it could be less, if you have applied less force, friction would maintain its small value. If you have applied the maximum force, which is equal to its limiting force, limiting friction, it will reach to that value. But the maximum value it can reach is this. Okay? So whenever we have a problem given, we don't really think about the weight. We find out the normal force in that problem. And if we have a normal force, then we can get the limiting value for the friction. When the object has started moving, it is called kinetic friction, Fk. and Fk is also equal to mu k n. Now I didn't put the less than equal to sign there. It is equal to that because now after the object has started moving, then it will maintain a friction. So this Fk will be equal to mu k n, where mu k is the coefficient of kinetic friction. Mu s and mu are not the same. Mu k is generally less than mu s because the object is already moving in motion, and that results in a smaller coefficient of friction. Good. Any questions? Okay. Then I have some questions. Does it have a unit? Mu s and mu k? Look at the equation and tell me, do they have a unit? No. Why? Because they both are forces, right? No units for them. You are pushing a book against a wall, something like this, pushing on it. Which way the force of friction acts? Okay. More answers? So he said it should be acting this way. Is that right? Do you all agree? Mm-hmm. Yeah. When you move your hand, which way the book will go? Right? So the friction was always acting opposite to the intended direction of motion. The intention of the object is to go down. So friction would, yes, he is correct. This is the proper direction. And the reason is the intention, the body is intending to go down. It's friction upward, keeping it up, right? And the weight is still mg downward. What's acting on it?
Would it be in the same direction as the friction because normal force is always opposite of gravity?
Okay, you mean upward? Okay. Force? Okay. So she says it's here. What do you think, Fiorella? Mm-hmm. There should be a surface, right? There must be a surface. We already know that the normal force arises due to the objects pushing on each other. So you are pushing on the wall. Wall is going to push back on the surface. Yes, this is the correct direction. This isn't. Okay? Come on, we are not done yet. No, we are done. So in next lecture, we will do now everything. Now you are introduced to all forces, normal, tension, and the friction forces. Now the problems can include all of them. Okay, so I will pick some problems which have at least 2 of those and solve them in the class. So next class and the class after that, they are very important for problem solving.